All right. So today is really about optical imaging, and I want to go over the core concept of optical imaging technique. So first, I want to discuss about what is optical imaging. In fact, what is imaging? In fact, so start with the general concept that what is imaging to us? Imaging is an act to figure out the spatial geometry or morphology of the object outside of the world and to make it sense to us. For us, we have a sensor called eyes and retina. So that is a kind of a screen. We want to have the object form exactly. Spatial organization will be mapped onto our retina to be able to recognize the outside of the world. So if I want to make that into this diagram, you can see, let's assume there's a tiger outside, which is, of course, we have to pay attention. How do we see this tiger onto our retina such that we can recognize the tiger, which may be a danger for us if we are in the wild space. So then you can think of, there are always lights, ambient light, which is coming, and then each of the tigers on object point, the light will interact and it will scatter out. Remember, scattering is a photon and deviate. Not only photon, kind of the particles deviate when it hits with an inhomogeneity. So there comes the scattering from one point. And somehow, if those scattered light is in imaging space, if those scattered light will focus down to another point, which is a point mapping in space. Let's say another point also focus down to another point corresponding. In this case, it's kind of flipped, but let's assume that doesn't really matter. Then we can have one-to-one mapping, and so that we can understand in imaging space what's actually seeing what's out there in the object space. So this is concept of a imaging. Okay. So in fact, imaging is this scattering process has to be somehow to turn into a focusing process in a manner that you can have a spatial relationship. So for this, in optical imaging case, we do need some optics or optical elements to undo the effect of scattering. And in free space, we should focus the light. So this is concept of what we call as an imaging. For that, we need to seek out what kind of optical element we can actually focus it down. So, and also the property of the light interact with an optical element. So for that, the basic one is its reflection and refraction at an interface when a wave interacts. In this case, of course, light. So you already learned about this from previous years, I believe. So there's an interface. We have refractive index of N1 entering into N2. And let's assume we have instance light, which is oblique angle. Then what can happen is, I said, at the interface, some will be reflected and some will be refracted and transmitted. But the angle will be changing. And if you think about the boundary condition of this electromagnetic wave, you will find out the reflection angle will be the same. This is so-called famous law of reflection. What about the transmitted wave? So you can think of this as having N2. Let's assume N2 is bigger than N1. What that means is the wave will slow down. So if we have a kind of a wheel, two wheel elements going in, and this part will slow down, so the wheel will change this direction and going this way. So this phenomenon is a refraction, and that relationship can be easily computed by calculating the speed of light change with respect to different refractive index. And that turns out to be n times sine theta has to be conserved. This is so famous that the law of refraction. And you already heard this is a so-called Snell's law. So what it here means, like previous class time, as I said, the wave tend to bend toward with higher refractive index. Here you see the waves going, and then it meets an interface because this is high refractive index, it bends toward the high refractive index. And this can explain mirage and looming effect last time, so that you can actually understand this. Of course, there are other ways how to explain this. So for example, let's say this is an ocean and this is a land. Let's say there's a guy here watching. If someone is swimming and lost and dying, so how this guy will go to this person to save him or her. The way, the problem is this is an ocean. Its swimming speed is much slower than running speed. Then the guy has to find an optimal path to reach the minimize the time so that the speed of V1 and V2 are known, and you can find this path, and that actually gives this interesting Snell's law. So this is a very interesting phenomenon. If you think about this, how to derive this, and there is a very interesting ways of interpretation of this Snell's law. Now, the phenomenon I said about imaging is really an object has to be onto our retina so that we can make sense of this imaging space out of this object space. So we said the light has to scatter from a point and it has to focus to the point of this imaging space. So that this is kind of our eye. In fact, we have a lens inside our eye. This is exactly how it works. So there's an object, let's say green light is the light emitting from or scattered from this arrowhead, and that has to be somehow converges. So diverging rays has to converge, and in fact, like the one I showed Snell's law previously, so this ray goes in and bend toward the high refractive index. When it goes center, it doesn't change, but it goes this interface, it goes towards more higher refractive index. That eventually means the light somehow converges and focuses down. Likewise, the rays, the light coming from the bottom of this arrow, some initially diverges, but through this lens, it bends towards this high refractive index, and likewise, it will converge to a point. So it's a one-to-one mapping of this point images onto image plane. So this explains what we are seeing and recognizing outside of the world. The light has to focus down onto our retina in a spatially consistent manner and one-to-one manner. However, that was inverted, note about that. So then we can ask ourselves, what is the ideal optical imaging system to us? For that, we already said there's an object. If there's a light, scatter the light, or if it's fluorescent object, emitted light from point by point, those light emission will be in fact going outside of the world like this diverging fashion. But if we have a proper optical element or imaging system, we can call it, it will match this one to converge down to each corresponding point and focus so that we can form an image. Then you can ask about, hey, then I can have infinity amount of information of the object space if I have proper optical elements. That's a very good thought, and we have to think about what can be a limitation for this type of ideal imaging system. So ideal imaging system means each point in the object should be mapped onto a single point in the image. The question is the fidelity or the size of this infinitesimal point can become again infinitesimal point, which means like infinity of resolution. So currently you can think of, let's say, these are objects are composed of molecules, and molecules composed of atom composed of like nucleus and electron. Yeah, those are objects. If you can map those one by one, you can have almost infinity of resolution. Why that is not possible? This is very important for whoever deals with an imaging system, talk about it. That's about resolution. So in the real world, the imaging system actually do not focus perfectly. That's a problem, and we have to know where comes this limitation. What do we, how we can overcome this limitation? Okay, so first of all, as I said, geometric optics, which we will talk about it, like the one with the interface and lens, that is very ideal. So it doesn't show anything wrong and anything which degrades the resolution of optical system. But remember that the light we are dealing with has a duality. Either it can behave like particle light, it can behave like a wave. Remember, all the waves having a property when it interacts with an object, it should diffract or bending property. So in fact, why we cannot get infinite amount of resolution by this optical element is first, we are using light as a medium, and light is a wave, possess a wave property. And when they deal with optical elements, these optical elements are finite. So it's a finite object. The wave will be diffracted as somehow. And that is a fundamental issue of optical imaging system. By using light, which has a wave-like phenomenon, because of that, there's a fundamental limitation of resolution. So the resolution really depends on the wave property of light, which is wavelength lambda. So remember, that's the key issue, that why we cannot focus perfectly. And of course, when you generate this optical imaging system, what happens is you cannot align it totally perfect. And also the lens over there, we manufacture the lens, and the lens is not usually perfect lens. The easy way to manufacture a lens is making the surface as a spherical way. So spherical lens we call, or convex lens. And that lens, if you use geometric optics, you realize the rays will not be perfectly focused down, because the surface of the lens, what we make a spherical shape, is not in fact ideal. So those imperfections in image formation we call aberration. In Korean, it's called sucha. So aberration can contain many aspects, but these two are the major cause of why we cannot have, let's say, 1 nanometer resolution, 1 angstrom resolution with an optical microscope. So this is something we want to have a fundamental, here a fundamental limit is of course a diffraction limit. Because aberration, somehow if you are using poor optics, you can use more expensive or optics. If it's a spherical aberration, you can buy aspheric lens, which is much more expensive. So you can actually reduce this aberration. But somehow diffraction limit means the light is bending when it interacts with an optical element. And that is a fundamental wave nature of light. So it's kind of hard to overcome. So because of that, let's deal with an ideal optical system first. And the scope of this lecture is really about that. So we want to first see how to, by using hand and rulers, we can make a simple lens-based optical imaging. So that's a ray tracing, and I want to draw this. Let's go follow. Let's assume this is a lens in our eye, and there is an object outside, and this is the image. All right, so the lens, and a lens has a focal length. As you remember that if you have a lens, sunlight, it's almost like a parallel collimated light because so far, and the rays, when you put a lens, you all have an experience that they can focus light, and they can be so hot that you can even make a fire out of this. So if object is there, you have a lens. The most important thing is you mark the focus. The role of focus is if the rays are parallel to the optical axis like this, and it must go through the focus. So the rays of this red goes like this. In fact, for finding where the image is formed, you only need two rays. Remember, the rays coming out of this point should become a point here. So you just need one more ray. So let's say we send a ray to the center of the lens, and then it's symmetric, so it doesn't have to bend towards either direction. So it just goes through and it keeps going. And some point, because this ray has bended further and this didn't bend, so they will meet at some point. In fact, this is the point where image will become forming. And another just auxiliary one, because this has a focal length here. What if the ray goes through this focus? Then because it's a focus of this lens, it will become parallel to the optical axis. So you will realize these three rays must converge it to a point, and that's where the point of this arrowhead. Then look at the geometric relationship of this object distance from the lens. Let's define as d sub 0, and the image formed, the distance is d sub I. Then from here, you can find the geometric relationship of a similarity. So for example, you can see the object, let's the height of the object as a HRO, and the height of the image as H sub I, then this is HO. And this follow this geometric two triangles, they are similar. And this is HO, and this is HI. And this distance is D sub O minus F, and this distance is F. And also, if you look at this similarity, and this ratio to this will be the same as this ratio to this. With this simple relationship, what you will find out is if you can remove d sub I and d sub O, you will find, and this relationship, oh, sorry, I think if you remove this H sub O and H sub I, because that ratio we call as how much elongation happens, and we define it as a magnification. So the height ratio will be magnification from the geometry of this. You can follow this triangle of this and versus this. So the ratio of HO to HI will be the same as ratio of D sub O to D sub I. So that is magnification. And with this relationship, you will find out a very famous relationship between when the object is this distance of D sub O, what will be D sub I? And the parameter should be this focal length F. So that's we call lens equation. A simple, easy way to consider this is, what if this distance is 2F and 2F, then you will find out this will hold. So if object is somehow twice farther from the focal length, then the image should be twice farther from the lens. Does it make sense? And in fact, from this image, what if this d sub o is in fact smaller than f? So let's say this object is smaller than f, such as half of the f. Then this term will be bigger than the left-hand side. That means d sub I, the sign has to be negative. And we'll talk about this later. So this is what you want to practice at home and try to derive this. This is very, very easy. And here we assume that the light is perfect. So point become perfect. But later I will tell you that, in fact, the information from the object, the scattering, the light will go elsewhere as well, even different angle. But remember, this ray will not pass through this object, and there's a limitation here. So this is a kind of block you can consider. The interaction of wave nature interact with the obstacle will bend the light, and that makes an obscurity in the image. That's what I mean, the diffraction limit. And that will cause the point will not be perfect at the image space. So now we know that how, with a simple one lens, we know how to make an image, okay, which is great. And now move one step further about understanding this traditional microscope, which is composed of a single lens over here. But those images will form somewhere here in the image plane, and we have to use our eye. Our eye has a simple one lens, so that you remember when you look at under the microscope, you see something like very big. So let's use our geometric optics to understand that here. So, and also I will discuss about real and virtual images of a light microscope. So this is a little complicated, so bear with me. So let's assume that we have one lens microscope. So one lens, we just made a geometric optics to make a form an image. So we need only two rays. This lens has f0 as a focal length, and object ray parallel will has to pass through the f0, and then another ray which pass through the center will not be disturbed because of this symmetry, and it goes, and you will find out there is an image form because of this convergence of the light. So now, so far so good. But now we have our eyeball, okay? Let's assume, let's assume this is an eyepiece over here. So eyepiece have this focal length, but the trick here is the image should be formed within smaller than this f of the eye piece, and that's the point. Then why this is important? As I described from the lens equation previously, if the object location to this lens is shorter than the focus or focal length of the lens, what happens is the rays coming out of this object, okay, will not focus on this space because they are eventually diverging. But we have to always think that how we perceive outside of the world is based on the direction of the ray, because they have to focus down onto our retina, or our retina should, we should recognize where comes this ray. If we have only these rays available, we are considering the rays coming like this far point where they were supposed to have a focus. So this is what we perceive. Remember, this is very similar to when we discuss about mirage, which is, in fact, it's not true that oasis, palm tree is not underneath the ground, but we can perceive that depending on how rays coming into our eye. This is exactly the same. Let's apply geometry of this one more time. So the parallel ray will pass through this f of focal length, f sub e, okay? And then the other rays like bend. The problem is this distance is shorter than this. So that means is the rays will not converge in this space. So here comes our eyeball, and our eyeball will perceive these rays to form an image over here. And we consider the object through our lens exists over here. Isn't it amazing? So that's how we actually see under the microscope. And here I want to discuss with you. Think about, let's put a film and see if there exists an image. So if we put a film over here, of course, the actual light will focus down, so you will form an image from here. So that's real, okay? However, we perceive this one as we perceive there exists this object somewhere there. But what if we put a film over here? What can happen? In fact, these lines are dotted line, which doesn't exist. It only exists after this eyepiece lens. This ray exists, but the other part doesn't exist. We just perceive it. So even if you put a curtain or a film over here, you will not get the image because this image is a virtual. So I want to explain here as this image can be seen on a screen placed in the image plane. So that's a real image we call. But after the eyepiece and to our eye, you cannot observe a viewing screen or record on a film over here. That is called a virtual image. So hopefully this makes sense to you. And so viewing an image in a microscope is, in fact, what about our retina? Yeah, this is a screen. The rays will actually focus down. So it's a real image. So viewing image is a real image forming on our retina, but it's perceived as a virtual image. It looks to us that there's a like flipped and big object exists over here. And that height difference is, of course, in the end, we call so-called magnification. So, and this one really shows that the outside of the world as what we see may not be always real. It could be virtual, like virtual reality. Okay, for this, I want to go to a little bit of a history, but the key aspect of understanding how light microscope works, especially not the geometrical optics, but the true fundamental limitation of a microscope. I said the fundamental limit of light microscope or any microscope we uses a wave as a medium. Okay, so there comes a Ernst Karl Abbe. Abbe was the person who first recognized and formulate and propose a theory of image formation. So let me first describe, for those who have maybe physics experiment in your middle school, high school, you remember you have a diffraction grading. Grading, what's interesting is it's a regular pattern, periodic pattern. If you send the light, then not only there is a primary light passing through, depending on the gradings period, the another light, diffraction light, will go the other direction, the other direction. This we call first order diffraction. But there are also second order diffraction and third, etc. So you remember that this diffraction grading, the angle difference really depends on the grading period. And he actually extended this basic idea of grading that, hey, we have learned about Fourier series analysis, that any wave pattern can be decomposed as a sinusoidal waves of different wavelength. Likewise, any of the object outside of the world, we can consider it as a composer superposition of gradings. So this might sound a little weird, but this is a fundamental insight into understanding the object. And we want to have an optical element or optical system to grab that information onto your screen. Let me reiterate. So you remember that grading pattern. If the grading is bigger, remember the diffraction when I explained, when the wave interact, the relatively it's a bigger object, the bending of the light is not that big. However, if the relative grading space is much narrower, what happens? The bending will be bigger. So what it means is the information of geometry of the grading period actually reveals the bending of the light. The smaller the feature, the bigger the bending of the light. So if we can capture the bigger angle with the optical system and grab them into the image space, we can achieve higher resolution. If the grading is coarse, then the bending is smaller, and we grab that information with the optical imaging system or lens, we can get that information. Hey, wait a second, what about really tiny grading? That tiny grading will lead the light to bend more. Too high angle, then our optics may not capture them. Then in the imaging space, we lost them. That's why we cannot image or get the information of very fine grading or fine feature. So we have a limited resolution. So that concept can be described here. So an object can be considered as a grading, and you send the light wave, and of course the diffraction order of 0 pass through, but there are first order plus minus diffraction and second order diffraction. But our lens is a finite that, let's say in this case, we lose the m plus minus 2. This is a higher order diffraction, and then these 1 plus 1 minus 1 will eventually form an image plane. So what that means, we may lose the higher order diffraction coming from fine, smaller features of the object. That's why our microscopic imaging has a limitation in terms of spatial resolution. And probably in the future, I will offer another class of biomedical optics. And at that time, you may grasp even more fundamental quantitative way, but this is what I want to explain you. Object can be considered and sum of gradings, and grading will diffract light, so that diffraction nature fundamentally limits our finite size lens cannot grasp high order diffraction. That's why those are coming from fine feature, and you cannot reproduce fine feature in your image plane. That's why we cannot image too tiny object, in fact, tinier than the wavelength of the light in general in our image plane. Okay, so that microscope image formation was recognized in 1873 by Abi, and his looks like this. And he was the first, if you look at history, he was a very interesting person who also made like a modern concept of a labor. So he made his workers in his company very well. So that's another of his contribution. But fundamentally, when he died, this is what into his tombstone. So D is in fact optical resolution. Resolution is proportional to lambda. Okay, so it's proportional to the ruler of the light, which is wavelength lambda, but it's divided by n times sine theta here, alpha. Remember n sine alpha I will discuss. This is called numerical aperture. You see this angle alpha actually means this angle of acceptance to the lens. So if the angle is bigger and bigger, then this sine alpha will be bigger, and so D becomes smaller, and you can image a smaller object or higher resolution. Okay, so if you name this theory, actually this is a quotation. So his insight for comments on the imaging is the microscope image is the interference effect of a diffraction phenomena, because these are diffraction phenomena, and these different diffracted light has to interfere onto your image plane. And so this famous theory we call diffraction theory. And this sets a fundamental limitation of resolution. So let's say we are using visible light, which is a several hundred nanometer wavelength. We cannot go below half of the wavelength as a resolution. Okay. So this one, so you can think of, hey, what about I'm using IR wave to do some imaging, and you can check out, oh, IR, are you using 1 micron wavelength? You can quickly think, oh, you may not be able to get below 500 nanometer resolution. Okay, so what if you can think of, oh my gosh, I'm using electron microscope. What's the resolution? Then you can think of, hey, electron is a particle, but electron can be considered also contains a wave nature. That actually led to Nobel Prize, right? Wave nature of the electron. And so electron can have an exquisite resolution because it's 10 picometer to 10 nanometer. So remember, electron microscope gives us a very good spatial resolution. So that led to the concept of numerical aperture, which I will show you n sine theta next. And that sets the resolution limit of a microscope. This was 1873. So for the past about more than 100 years, we were just talk about this idea. But it was only until the early 2000s that people are coming and to say that, hey, we may overcome this diffraction limit if we use a trick. Okay. For example, if we can focus light even smaller than diffraction limit in object space, then we can potentially have that resolution. Hey, if we can have a nice pattern onto the object where the pattern size is smaller than the wavelength, then we can get that resolution. This actually led to the discovery of breaking the diffraction limit of a light microscope, so that now we can have not only 100 nanometer resolution, we can have a tens of nanometer resolution. And of course, that led to the Nobel Prize of 2014 in chemistry. So, you know, it's very important to understand the fundamental limit. It's even more important to think of where comes that fundamental limit and how to break that down. Okay, so because of that, when we talk about resolution, I want to introduce a term which was coined by Ernst Abbe, I just showed. So that's called numerical aperture. And why, you know, in camera, there's an aperture. And that's those who like to have a taking photography, you can also understand. So you have a smartphone that has a lens that's a tiny, and that tiny lens do not provide us high resolution. But remember, some photographers, professional ones, will have a huge lens and take a very sharp image. And where comes that sharpness? Because this aperture is big. So that we call numerical aperture. More specifically, not only the absolute size of the lens, but from the object to the lens, this angle, halfway of this from the middle, this angle theta is 1 meter. The bigger, because of, remember the diffraction, this is kind of the maximum angle of diffraction which pass through this optical system, eventually focus down onto your film. So that angle is very important. And not only this angle, remember, if there is a refractive index medium over here, that can actually increase the effective information of diffraction here. So that we call n times sine theta max. Here is a theta max, and that's defined by Abbe. Hey, this is fundamental parameter which can decide the resolution of your optical microscope or image. So that he named as a numerical aperture. I'm not sure why he put the numerical, but it's not just absolute aperture size. but this ratio and that angle does really matter. Or maybe there's a refractive index n. Maybe this n comes from here. I don't know. But anyway, this is very important. And if you look at it, it's dimensionless because the refractive index is a ratio, non-dimension, sine theta is non-dimension. So then what's the important thing we have to understand for getting high resolution? So you see there's an aperture stop over here, physical element, which is like iris, okay? So if you want to have high resolution, you increase this iris or aperture as big as possible. But if you don't need that, this means that there's enough of the information or light collection is happening. But what if you reduce down the iris? Like when you are in a too bright place, you want to make your iris shrink. In that case, in fact, you are losing your spatial resolution. So what's the meaning of this numerical aperture? And NA, limits the optical information entering the imaging system. As I described you, the diffraction, the final information or final grading will diffract further and that will be lost. So this numerical aperture is really about the optical information content which passes through your system. At the same time, the bigger this angle, the more information of diffraction and you have higher resolving power or resolution. So in fact, I want to show how point will form an image on your image space. So let's say there's two cases, low and high NA. Low NA will form a tiny, let's assume tiny point formed here versus here. And in fact, this is not point anymore. It looks, I plot this one as a 3D. And if you look at under the screen or your camera, it looks like this, like disc with this shape. So that was discovered and named by Airy. So we call it as an Airy disc. So the size of a central disc really determines your optical resolution because tiny point become this disc. So the smaller disc here, you have high resolution that actually comes from high NA. So with a larger numerical aperture, you collect more light, and so you have a brighter image, and you have a better lateral resolution. But what are cons of this? Because of this high angle, you only can focus at the focal plane, but out of focus, you actually quickly lose your sharpness. So it will be blurred. So shallow depth of imaging with the maybe the other aspects of large NA, but it can be used by photographer that now have a nice picture, you have a nice focus at the object, but blurring out the other side. That can be artistically utilizable. So remember the tumor body, there's an n sine theta, and that n is refractive index of this medium. And that is related to resolution. To increase NA, you have to increase n from 1 to even bigger number. In the air, the refractive index is 1. But what if it's inside, immersed in the water, refractive index 1.33? What about in the oil? Then it's even higher. Refractive index is 1.52. So that you can even increase your resolution 50% of the time. So that's what I want to show. So that's where immersion oil is coming and it can increase resolution. And I want to show you why from this picture. So look at that. So this is microscope objective lens. And typically you have microscope slide and you have very thin, small specimen, and you have a regular microscope covered glass here. So what happens if there is a object for space is air versus, let's say, oil in this n equal 1.5 to 1. The rays coming from here, from the Snell's law, it will bend towards this way because this is a low refractive index compared to glass. Glass has almost 1.5 refractive index. So what happens is it bends towards the outside. And so this ray eventually turns outside of lens and you lose that information further. So this has a limitation. What if you fill this with an oil, which is matching refractive index, then actually this ray is now keep passing through until this angle. Because previously that angle is so high that they didn't even go through. That's why this one provides you more of a spatial information or spatial resolution. Hope that makes sense. So typical refractive index of oil is 1.515. So index matching is very important. If you are an aspiring cell biologist, you want to watch and observe a subcellular domain, which has a size of 1 micron level, then you have to use this high numerical aperture objective, and most likely you have to use immersion water or oil, okay, so that you can match and having higher refractive resolution. I want to just show you, this is cartoon, so this is reality. This is objective lens, and this is microscope slide. I think it's 1.2 millimeter. And in fact, this covered glass, it's not on scale. This is usually thickness of 170 micron. So that's like this thick, very, very small. And what about the distance of object lens to the specimen that we call as a working distance? You know, in this case, working distance is only 230 micron. You know, this is, you cannot even see very well with your eye. It's a very, very teeny tiny. And so, and the most expensive part is objective lens. So you gotta be very careful when you do this high resolution optical imaging, because even small displacement in the wrong direction can break your sample, and even worse, break your objective lens too. Okay, so hopefully, so the rule of thumb is, in practice when you do experiment, you go to as close as possible and then only move the other direction to find the focus. That's a practical tip. So how to increase numerical aperture to improve resolution? So if you can increase resolution, you need to increase numerical aperture. So people have thought how to increase. First, you want to increase this angle, which means you have to have a bigger lens. Okay. And the other is you need to use this medium as a higher refractive index, such as oil in this case. Does it make sense? Hopefully, this one makes sense. So, so then when you actually take an image, you need to somehow quantify and define the spatial resolution. So how can you do that? So now let's think about, what do you mean by resolution? So resolution in an image is somehow images, most of the time, it's not exactly the object itself. It's always blurred, like this diffraction nature of the light. So the blurred one, if you can consider two objects to looking at like this, you can see, oh, there's two objects there. Then you can say, I can resolve these two objects. What if they are closer? Okay, that's a little hard, but it's still, I think I can resolve. I can see there's two objects. What if they are even closer than that? Oh my gosh. If you don't know anything about the object, if you look at this, can you consider there's two objects over there? Probably not. So this means we cannot resolve it anymore. So we want to define the minimum distance of 2-point object, which can be perceived as or resolvable as the resolution. So, you know, this is only one kind of a proposal, but the resolution can be defined any other ways. But I'm talking to you the most widely acceptable. So if you look at the profile of the light, this looks like this. So these are area disks resolved, and this one, hey, there's no way for you to be able to tell there's two objects. So you cannot resolve. So it should be somewhere in between. And we want to define that the right distance as a resolution, and the Sir Rayleigh, in fact, defined this on first time. Because this profile of the 1 point, or we call point becomes spread. So we call point spread function. So this a line, field line, you can see this is the profile. So interesting, because it's a wave phenomenon, it has interference. It looks like this ringing effect, but it goes down to the first zero. And how about if the other object just sitting on this first zero, like this dotted line, then if you plot it, that is exactly what's over here that it looks like. So this is an easy way to define the resolution. Hey, let's define our resolution from the center line to the first 0 point of this point spread function. That's what Rayleigh said, and that we call here from the center, the first 0, and this is Rayleigh criterion of resolution, and you can actually analytically calculate, and you can formulate this one. And that formula gives this resolution is, in fact, 0.61 lambda over NA. This one, you can remember it, but this number is so difficult to remember, you can consider just half of the wavelength. And there's a NA numerical equation. But in practice, you know, because this is noisy in your actual practice, it's hard to find out this point. So instead of this, what you do is from this background level to the top level. So how about this, just half of this? So from the top to bottom, just exactly half position. Let's cut through and then find out the width. So that's actually what we practically use for defining resolution. And this one is similar to this, okay? So that in this case, why it's similar? If you consider this as a just triangle, this distance should be twice of this. And so twice of this, and this distance is almost similar to Rayleigh criterion. Hopefully this makes sense, and that's spatial resolution. And now I want to discuss about imaging to us. What do we mean by imaging? Think about your drawing. Let's say you are an artist. You are in an art studio, and let's say you are drawing a nude object. Those who have done this will find very difficult to draw human body if you don't have a proper illumination. What do I mean by that is, like human body having this smooth surface, it's very hard to make a sense unless this outside of the edge. So likewise, when we understand an object outside, without proper contrast, we cannot even recognize. So what provides us three-dimensional information to us is really the contrast. So contrast is the information of an object relative to the background. So that's the key concept. And when you talk about image, let's say, how do I know some object is here? Because there is the information here stand out from the background. If they are both very bright, then we may not be able to see this one clearly. So contrast is everything in an image, okay? So here I brought an X-ray images, for example. So it's not like optics, but X-ray is also electromagnetic radiation. But I want to bring your attention about contrast. So you see there are objects with bigger to small size, but the level of intensities are different. And the bottom background is kind of hazy or noisy. Okay, so you can say, oh, this one you can see clearly, high contrast. This one very hard because they are very similar, low contrast. Maybe there's medium. So this is what I mean. Even if the objects are the same there, depending on the level of the signal level with respect to the background, you can define as contrast. So the meaning of contrast is really about the differences of signal from your object from the background. So that really is a difference. So the visibility of a structure in an image really depends on, among other factors, its contrast. And you can define contrast as a difference between signal to the background. So it's delta I. I have to say, if you look through some other textbook, contrast may be defined even differently. In fact, a year ago, I defined contrast differently. I defined contrast as a ratio of delta I with respect to I sub signal level, relative one. So, but I changed my mind because this is making more sense in the end to me. All right, so nothing's absolute, but you can choose what definition makes more sense to you. Okay, so for that, we know a lot about signal, so or electrical engineering or whatever in field we talk about signal versus noise. And signal and noise, of course, is also important in imaging. And I want to narrow down our scope into an image. So what is signal and what is noise in the image is always the question. And in reality, in real experiment, in real world, there's always noise exists. It's not like ideal world, but that's a fundamental limit, I have to say. So I actually brought a figure of my paper, which is done like 14 years ago. I published my microscope, which was supposed to be super resolution microscope. So you look at this, what you are seeing is actually actin filament bundle in NIH 3T3 fibroblast cells. So we are looking at the actin filament bundle inside the cell. And this is a microscope with a wide field microscope. And I choose these two lines to see what it looks like. So this cross section is like this, and the other cross section is like this. So what do you see here? Overall, you can see there's some object here, maybe some over here, which shows up as here and here. And what you notice is, what about the other part? The other also goes something going on, but that's very, very noisy. And that is a background noise. So from here, you have to somehow interpret your image. Which ones are actual actin fibers, which ones are background. So here's the real issue of contrast. So contrast do not represent fundamental limitation. Contrast is just the level difference of signal versus background. It's a very much important visualization, but it may not provide you fundamental limitation because contrast, you can have some instrument which enhances contrast by just amplifying your signal, but it may not fundamentally resolve your information because contrast can be artificially enhanced. Or in this image, you can just subtract digitally from 0 to here, okay? This way, you can relatively increase contrast or thresholding or raging intensity. Even you can increase the power of light to increase the contrast. However, I have to now focus you about the noise. Noise is sometimes more fundamental. So statistical noise actually puts a fundamental limitation on you to be able to make sense of your image. So from here, I want to give you a definition of signal, contrast, and noise. So, I mean, this is the way I interpret. So let's have this a big fiber bundle, and that level from the bottom, let's assume this is 0, although there's a little bit offset here. Let's assume this is 0. So that blue arrow size is signal, okay? However, you also notice the background is not 0. There's like this background's average level, which is dotted line, which is with this color. And from here to here is really the difference of signal to the background. So that this arrow is contrast. And the important thing is, what about if the noise is big, then it's going to be more obscure. So that noise level of the background, how do we represent this like random look like noise is an issue. And a simple way is from this, the standard deviation of background would be a good linear scale of the noise. So that I represent this double-headed arrow. Okay, then you can ask yourself, okay, I know that the noise is fundamental because sometimes if noise is even bigger than the signal, then it might be very hard to distinguish what the signal is. But the noise is more like random. It comes from its randomness. So I don't have much time to explain all kinds of noise, but I want to explain you three very fundamental important noise in optical detection. First of all, photon shot noise, so which is like when you detect something which is not continuous but in a discrete level, such as the light. It looks to you, if a lot, then it looks like continuous, but when it goes to dealing with a very tiny amount of light, the light behaves like photons, like a raindrop outside. You want to measure the average raindrop. What happens is you can have a mean value, but the raindrop's nature is kind of independent discrete level. There's a fundamental fluctuation. And that fluctuation we call shot noise. Or another way is we describe it as a Poisson noise. You may have heard it if you are an engineering student or signal processing guy or physics. So photon shot noise, I have to say, we are dealing with the light as a wave, but also at the low level, we are dealing with the light as in photons. And that photons nature of this discrete detection phenomena fundamentally involves with a natural fluctuation that we call photon shot noise. And I have to say this noise is proportional to the square root of signal. Just remember that once. It will be very, very much important later on. And another is we are using a detector, which detectors fundamental one is the detector, we are using electronic device, and that has, with a finite temperature, we have always thermal fluctuation, and that provides also noise that we call thermal noise or Johnson noise. So that is another, that's why many times you cool down your instrument to reduce down this thermal noise. And also dark current noise is always existing as you have longer exposure time, linearly increasing your noise. So these are like kind of three typical noise sources. It's good to hear once at least. And then the fundamental things about every time you do take signal, you have noise, and how you can explain the quality of your image. A good way in general is you talk about signal to noise ratio. This is of course in other fields such as telecommunication and other fields always talk about signal to noise ratio. So it's better for me to just give you an example. So here, there's signal here, there's a square, but it's very obscure and hard to know because in fact the signal level is actually smaller than the level of noise. So something's there. What if the signal level is comparable to noise level? Here, I define noise as standard deviation of the background. Okay, there's something there, but it's very, very hard. In fact, we are visually seeing, but if you look through this profile, it looks almost like this. Oh my gosh, how can you know what's going on over here, right? Because signal to noise ratio is about 1. So to be able to reliably detect an object, in general, we call signal to noise ratio should be bigger than 1. For example, like this 2, you see something's over here compared to the background noise. Hopefully that makes sense. That's why not just ideal theory, but just the reality and real experiment, you have to take care and consider about the nature of the noise. And in fact, this is a little advanced, but I want to show 2 examples of the noise. If you look at this profile, there's a signal level, but also it involves noise. And this one, it involves noise. But these 2 show 2 kind of different nature, different category of noise. This one, you see the level of noise, even the signal level is high, the level standard deviation of noise remains the same. You notice that? And the lower one, you look at that, when the signal is higher, you see noise is higher too. And both of these you have to understand when you are dealing with this imaging and image analysis. And I have to say, this constant amplitude noise is more likely to coming from electronic noise. So it doesn't depend on the level of the signal, okay? However, what's interesting here is that this some noises are depending on the signal level. In this case, you see noise is higher when the signal is high. Good example for this is that photon shot noise. So if you have higher level of signal, the level of fluctuation goes too high. In photon shot noise case, the level of noise is higher to the square root of the signal. So hopefully you understand that. And how do we define signal to noise ratio? Yeah, you can define that signal level with respect to the background noise. That's a good way. So that's how we define. So average signal in your region of interest divided by the standard deviation of the background, which is actual root mean square value of the intensity fluctuation of the background. Hopefully this will set you having some understanding. But the last thing, I want to describe you about even more important thing to us, because even if there's a signal and noise, what if the background level is so high that it's hard to distinguish what the object is in relation to the background. So the difference is really important in that aspect, okay? So that I call it contrast. So I want to define contrast to noise ratio, which is actually more important for us to perceive in an image. So here I brought a simulation from this website. So this is noise level 1, 2, 3, 4. And remember, contrast defined by signal level difference to the background. So the contrast can be 1, 2, 3. You see, of course, this 1, 2, 3, contrast to noise ratio 3 to gray. If contrast to noise ratio below 1, you start to having difficulties figuring out. So when we talk about determining the image quality, especially visualizing or perceiving the presence of object shape with respect to background, better to use contrast to noise ratio, because ultimately the ability to visualize a structure depends on the contrast to noise ratio. Or let's say you are a radiologist trying to find out tumor in your X-ray image. You want to detect that lesion or tumor, you really depend on contrast to noise ratio. Then how you define contrast to noise? It's easy. You divide contrast to noise level. The noise level you can use background standard deviation. But what's contrast? That's a signal minus background. Remember, we just described signal to noise ratio as not having subtraction of this background. So here I want to explain you. So when to use and how can we know the difference between signal to noise ratio versus contrast to noise ratio, specifically in image analysis. I have to say this definition can be different or more refined in different areas, such as, let's say, image, vision science, image processing field. It can be defined different. So you have to also understand that category of this explanation. So simply, SNR versus CNR is signal divided by noise or contrast divided by noise. And what do I mean by this signal and noise? It's more like when there is an image, let's say you know this is an object of interest, you want to have a region of interest, or in the signal, the average pixel and the standard background of region of interest. That's SNR. What about contrast to noise ratio? Exactly the same, but just as instead of signal, you have to subtract the background average, which makes you as a contrast. Does it make sense? So to make it even further understanding, I brought two examples here. So let's say like this one, you know, roughly there's some round objects over here, but it's kind of noisy, both of them. So you define your region of interest in the signal, and that's how you calculate, and region of interest in your background. And so if average signal strength is 150, let's say, and standard deviation of this background was 10, what's the signal to noise ratio? And by definition, the signal divided by the noise. It's 150 divided by 10, it's 15, which is pretty high. But like in this case, the background is a little high. So if the average of the background is almost 100 instead of 150, what's a contrast to noise ratio? Then you have to subtract 150 of signal minus the background level 100. So that's a 50 divided by standard deviation background of noise. This is fine. So this is how the difference is. Even if the signal to noise ratio might be big, but if the background level is high, then you may not have as high contrast to noise ratio. Eventually, the ability to distinguish signal to background and the object depends on the contrast to noise ratio. But if you look at many websites and literature, you will find out this may be used as interchangeable. So often people just say signal to noise ratio, but the signal, you look at the profile, they actually mean the contrast. So even if it can be confusing, just bear in mind that contrast often considered as signal, because sometimes people just subtract the background and then use it as a signal. And subtracting background makes it really a contrast. Okay, hopefully this makes sense. And now I want to describe another concept, very important concept for field of view in an image. Those who are using an image for your research should know the concept of field of view. It's very easy. So you have this object with this is called big field of view. This is small field of view. Okay. So field of view is an image referring to the extent of the image field that can be seen all at once. But in general, like if you have small field of view and then you expand for your presentation, let's say there's an original and you have chosen the small field of view, then this is how it looks like. So this is called digital zoom. And in fact, the information of pixel is there. So this is digital zoom, while if you really use an optics, so-called optical zoom, you still have fine information over here. Okay, so these two still have the same field of view, while the resolution will be different. So for example, zooming in a camera like this, and you actually compromises field of view for the resolution. And how do you determine field of view of an imaging system? Or more, let's say you are writing a paper, this is a figure. Any figure in your paper or report of an object of obscurity, you should put scale bar. This is very, very important. Because, for example, in this case, this object, this animal could be mouse or rat. But you know, rat is 10 times bigger, heavier than mice. How do we know from the image? No way. Without the scale bar, oh, this is 1 centimeter, so this must be a mouse. So scale bar is very, very important when you are presenting and interpreting any image, okay? And how do we know the field of view? Now you have a scale bar of 10 millimeter here. So overall here is about, let's say, 30, 40 millimeter. This is 40 millimeter. So that field of view is, let's say, 35 to 40 millimeter. What I mean by that millimeter is the ruler, the scale of the actual object space. That is field of view. So whenever you present your image to report, write paper, you must at least mention the field of view or put a scale bar so that readers automatically understand. All right, the next is about frame rate. We also care about dynamics of the sample if the sample is alive. So, or live or dynamic. So imaging speed. So we call it frame rate. It's very easy. How many frames per second? And remember those who loves watching YouTube movie or movies, our human eye cannot resolve transition of image that fast. But over certain higher frame rate, the animation appears smooth at how we can perceive and understand the movie. So that is about 30 frames per second. In the past, we also used 24 frames per second to make a movie. Even now, like even higher one, but about 30 frames per second or higher, we can actually see, we call it as a video rate, because now we perceive it as smooth, as a natural animation. But the real question is, people ask about what's the right frame rate for real-time imaging. We call like sometimes paper title, or we developed a microscope that can be fast enough for real-time imaging. What do we mean by real-time? In fact, real-time just means it can be anything. So very important. Video rate is specifically over 30 or the same as 30 frames per second. So real-time imaging do not have specific definition. Why? Let's say I'm just moving and you are watching my movement. So because this is a video rate, you are seeing me moving in real time. But if we are doing study under the microscope, the movement of cell receptors on top of the cell surface, they are so slow. So if I take image, 1 image per hour for over 2 days of tracing and chasing the receptor movement on a sticky surface, even it's a 1 frame per hour, we can claim it real time because the objective is moving that slow. So it's a relative concept. I hope you understand this is a real time imaging concept. And as I first say in the class, eventually imaging is about contrast. Okay, how do we perceive, understand the object from the rest of the world is really about generation of contrast. So imaging, we can define this way. The process of mapping a certain physical property or even chemical property of the object, and you want to display it in a visual form. So there's some property you want to actually visualize, and that property we call as a contrast mechanism. So for us, what kind of contrast mechanism could be important to visualize? For example, like absorption property of the light or pigment of the object, such as light imaging, typical bright field microscope, we are depending on this absorption of the sample. Or even X-ray is absorption of the bone, especially. What about scattering as a property? For example, cellular organelle has a scattering, and that reveals the presence and shape of the organelle. Then we are using scattering as a contrast. A good example is phase contrast microscope. And sometimes we want to tag with the fluorescence level to, let's say, mitochondria or DNA. Then we are using fluorescence imaging. Then we are using fluorescence emission as a contrast mechanism. Or sometimes we are using ultrasound or photography. Typically, you are depending on the reflection light from the surface, and then we visualize the surface of an object. So we are depending on using reflectivity of an object as a contrast mechanism. So typically in microscope, we are interested in intrinsic nature of the specimen, especially absorption nature, scattering nature, and sometimes emission of specific target or quantities of our interest. Here I want to explain one note about resolution versus contrast in optical imaging. So when we call resolution, is really fundamental nature of an optical instrument itself. While when you prepare your sample, let's say you have poorly stained the sample fluorescence that it doesn't show up. It's irrelevant to the microscope, okay? But you have poor image and you cannot distinguish that has poor contrast. So in that regard, contrast is not only depending on the instrument or microscope, but also sample. So that's what I want to focus. Let me summarize today's, this week's of 1 week, but this can be a semester course of biomedical optics. We start with a nature of the light with a particle wave duality. This sets a fundamental limitation of our imaging resolution and the characteristic of light refraction, diffraction, and interference. These diffraction and interference is how we can form an image in a microscope and your retina, how you are seeing the world. And for that, we need to understand light and tissue interaction, especially scattering, and what wavelength of the light would be great for us to image underneath the tissue that we call near infrared window. And we have done geometric optics from refraction to generate a simplest geometric optics using simple lens, which is, of course, your eye does this all the time, and talking about real and virtual image. And I showed you how optical microscopy works especially diffraction and interference, and how to get high resolution, because resolution depends on numerical aperture. And I showed you how to define resolution based on the point spread function and image characteristic as signal, contrast, SNR, CNR, and field of view, frame rate. And eventually, everything about imaging, not only optics, is really about contrast. We want to extract the information of the certain physical property to make sense to us that we call contrast mechanism. All right, thank you very much for your attention, and